In the previous session, we have discussed two cases, that is x square is equal to 2 and x square less than 2 for the existence of square root of 2. In today's class, we will be continuing with the proof of establishing the existence of square root of 2. That is, we will be taking the case when x square is greater than 2. So, let us look at the proof. We are taking case 2, where we assume that x square is larger than 2. So, in the previous session, we had discussed x is equal to supremum of the set S. So, if we could establish that there exists at least one integer, say m, such that x minus 1 by m is an upper bound of the set S, definitely that becomes a contradiction, because our assumption is that x is the supremum of S and it is the least of all the upper bounds. So, if we could establish that there exists at least one number, say x minus 1 by m, whose square is also less than 2, then we can establish, or it is greater than 2 actually, x minus 1 by m the whole square is greater than 2, then definitely x minus 1 by m becomes an upper bound of the set S, because our S was the set of all real numbers whose square is less than 2. So, if we are successful in establishing x minus 1 by m the whole square is larger than 2, it contradicts the assumption, or it contradicts the fact that x is the supremum of the set S. So, that is what our proof technique here is. So, let us see if we are able to successfully establish that x minus 1 by m the whole square is larger than 2. So, we begin with x minus 1 by m the whole square, which is equal to x square minus 2 by m x plus 1 by m square, and that is definitely greater than x square minus 2 by m x. Why? Because 1 by m square is a number which is greater than 0. So, we have a small positive number being added here. So, this term is larger than this. Why? Because m belongs to the set of all natural numbers, and hence we have 1 by m square to be greater than 0, and therefore this holds. So, in order to have x minus 1 by m the whole square greater than 2, we need what? X square minus 2 by m x to be greater than 2. Or in other words, what we require is x square minus 2 is greater than 2 by m x. Or in other words, keeping 1 by m on one side, this is less than x square minus 2 upon 2x, or equivalently m should be larger than 2x upon x square minus 2. Now, we look at the assumption that we had started with. Our assumption was that x square is larger than 2. So, definitely x square minus 2 will be greater than 0. So, since our assumption was x square greater than 2, x square minus 2 is positive, 2x is definitely greater than 0, because we are discussing the set of all positive real numbers whose square is less than 2. Therefore, we have this entire term to be a positive real number. So, if we are successful in finding out a natural number greater than this positive real number, we can backtrack and show that this is a contradiction. So, how we can ensure the existence of such a natural number? We can apply Archimedean property. There exists such an m larger than 2x by x square minus 2, and hence using that m we can show that 1 by m is less than this, and backtracking we will be showing that x minus 1 by m the whole square is having a value larger than 2. Hence, we arrive at the contradiction that x is the supremum of S. So, using the cases 1 and 2, we have excluded the cases that x square is greater than 2 and x square is less than 2. Both can be excluded, and hence what we have is, we have x is equal to the supremum of S has the value x square is equal to 2. We have excluded both the cases in the law of trichotomy, which is against x square not equal to 2, and so x square should be equal to 2, and hence we establish the existence of square root of 2, and hence the proof. Now, if the set S in the proof of the theorem is replaced by the set T, that is the set of all rational numbers for which the same condition is applied, r square is less than 2, then we can see that y is equal to the supremum of t satisfies the condition y square is equal to 2. As a subset of R, if we consider this, definitely by the completeness property it do have a supremum, and that is y supremum of t, but we can show that y does not belong to the set of all rational numbers, because we have established the result that root 2 is an irrational number, and hence we establish that Q does not possess the supremum property, or in other words completeness property, and this shows that Q is a field, but it is not a complete field as in the case of the set of all real numbers. Now, we have the next important theorem in real analysis, which is called the density theorem, which says that how we can arrange the set of all rational numbers and set of all real numbers, set of all irrational numbers. So, the density theorem says that between any two real numbers there definitely exists a rational number. So, in other words, the theorem states that if x and y are any real numbers with x is less than y, then there exists surely a rational number between this x and y. So, the rational numbers are so tightly packed, that is the meaning of this result. That is why the name comes as density theorem. Now, let us look at the proof of this result. The proof of density theorem. The statement is given as, if x and y are any two real numbers with x is less than y. So, x is less than y is a condition given. We have to establish that there exists a rational number between these two real numbers. So, without laws of generality, we can assume that x is greater than 0. Then we have y minus x to be a positive real number. So, y minus x is greater than 0. And we have seen in the previous class that the set S is equal to set of all 1 by n, where n belongs to the set of all natural numbers, has infimum equal to 0. So, we have seen as the corollary of the Archimedean property, and therefore, if y minus x is greater than 0, definitely it cannot be a lower bound. There exists a number, say m, such that, or n, we can say there exists a natural number n such that 1 by n is less than y minus x. Because we have taken y minus x to be greater than 0, definitely there exists at least one natural number such that 1 by n is less than y minus x. So, that shows that 1 is less than ny minus nx. So, this indicates that nx plus 1 is less than ny. Now, x is given to be greater than 0, or x was assumed to be greater than 0, and we can have what? We can have by corollary 3 of Archimedean property, nx is greater than 0. Therefore, by corollary 3, for every positive real number y greater than 0, we were able to establish there exists a natural number ny less than y less than ny for every y greater than 0. So, this result we have already established in corollary 3. So, we can apply that for nx. We will be getting there exists a natural number, say m, such that m minus 1 is less than nx less than m. So, what do we have now? We have m less than nx plus 1 by taking the left hand side of this inequality, and we have nx plus 1 to be less than ny. Therefore, we have m less than ny. So, using these two inequalities, we get nx less than m less than ny using inequalities 1 and 2. So, inequalities 1 and 2 combined, we will be getting the result that nx minus m, nx is less than m, which is less than ny, because we have nx less than m on the first inequality, and we have established that m is less than ny using this result. So, we have m less than ny and nx is less than m implies nx less than m less than ny. Therefore, dividing throughout by this n, you will be getting x less than m by n less than y. And what are m and n? M and n are natural numbers, and hence they are integers. Therefore, m by n is considered as a rational number. So, your m by n is nothing but the r that we wanted to prove. So, between x and y there exists a rational number, we have proved. Now, using this density theorem, this shows that between any two real numbers there exists a rational number. So, this shows how densely the rational numbers, this is known as the density theorem of rationals over the real numbers. So, this shows that how closely the rational numbers are arranged. And using this theorem, we can establish the next result, that if x and y are any real numbers with x less than y, then definitely there exists an irrational number as well, such that x less than s less than y. So, between any two real numbers there is a rational number, and between any two rational numbers there is an irrational number as well. So, the proof of this is also very simple. It follows from this proof. So, proof of corollary. By density theorem, we have established that if you have, say, x root 2 and y root 2 are two real numbers, such that x root 2 is less than y root 2, then the density theorem says that by density theorem there exists a rational number between x root 2 and y root 2. X root 2 is less than r less than y root 2. Therefore, x is less than r by root 2 is less than y. So, what is r by root 2? R by root 2 is an irrational number because square root of 2 is an irrational number. So, r by square root of 2 is your s. So, we can even take x by root 2 and y by root 2 to be two real numbers, and we can proceed the same. We will be getting s is equal to r into square root of 2. So, we can take any of two real numbers accordingly, so that we will be getting an irrational number. So, it is not always mandatory to take x root 2 and y root 2 itself. So, this result follows from the density theorem. And another result which follows from the density theorem is, suppose u is greater than 0 is any real number, and if x is less than y, then there exists a rational number r such that x is less than r u is less than y. So, the proof is exactly the same as we have just now seen in the case of irrational numbers. It is given that u is greater than 0 and it is given that x is less than y. So, we need to take, so the proof of the third result is like this. It is given x is less than y and it is given u is greater than 0. Therefore, if we take x by u and y by u, the inequality remains the same because u is given to be greater than 0, 1 by u is also greater than 0. So, x by u is less than y by u. So, applying density theorem, there exists a rational number r belonging to q such that x by u is less than r less than y by u. This is guaranteed by the density theorem. So, this shows that x is less than r u is less than y as required in the question. So, that is the proof. Now we can establish some representations of real numbers, namely binary and decimal representations. A real number can be represented as 0.a1, a2, etc., an, etc. if all these ai's are either zeros or ones, then it is called a binary representation, and if all these ai's are either any number from 0 up to 9, 0, 1, 2, etc. up to 9, any of these numbers in any order, then it is called a decimal representation of the real number x. And we can express any real number in terms of either a binary representation, point a1, a2, etc., an, etc., where all these ai's are either zeros or ones, or in terms of decimal representation as 0.a1, a2, etc., an, where these ai's are any numbers from 0 to 9. And this representation shows an interesting result that every rational number has either a terminating or a periodic decimal representation. So, what is called a terminating representation? It stops after a few terms. Or it is a periodic decimal representation. Periodic means it is repeating in a definite period. So, for example, we can take the rational number, say 1 by 2. 1 by 2, as we all know, has a binary representation, has a decimal representation 0.5. It has stopped at this level. Then another decimal representation is, say, 10 by 3 if you take. 10 is a natural number, 3 is also a natural number. So, 10 by 3 is definitely a rational number. 10 by 3 if you take, we get 3.3333 and so on. So, this is what is called a periodic decimal. So, we can see that every rational number has got either a terminating decimal representation or a periodic decimal representation. So, that is a method by which we can identify a number to be rational or irrational. That is why we have pi, e, etc. to be irrational numbers, because they do not have a terminating decimal representation. Okay. Now, as an example, we can show or express this as a rational number, because we can see that this is exactly a periodic decimal, because we are having 2.31 41414141 is getting repeated. So, this is the periodic decimal. So, how we can find the corresponding rational number is, we express the number as 2.3141414 etc. to be, say, x. So, you have 141414 is the repeating value, and this is in the which place? If we take 10 times x, you will be getting 23.141414 etc. If we take 2 decimal places also, that means 1000 x if you take, you will be getting 2314.141414 etc. So that the difference of these two, if we take, we will be getting 1000x minus 10x gives you 2314.1414 etc. minus 23.1414 etc. so that the entire decimal places gets cancelled, and this side you will be getting 11 minus 2 9, this is 2291, and this when you subtract you will be getting 990x. Therefore, you are getting 990x is equal to, the value was 2291. So, 2291. Therefore, x is nothing but 2291 divided by 990. So, this is the method how we can find the rational number corresponding to a decimal, periodic decimal given. So, likewise, we can find any of the rational numbers which are given as an infinite periodic decimal. Corresponding rational numbers can be found out. Similarly, we can express a rational number as an infinite decimal as well. So, that is for today. Thank you.